Hello and welcome back. Today we're going to tackle velocity time graphs. We've looked at position time graphs and what we can glean from those. So let's take a look at its derivative in terms of time. So to begin, I have this lovely graph in front of us. The x-axis is time, and the units are seconds, same as the position time graph. But the y-axis is different now. It's velocity, and its units are meters per second. So what can this graph actually tell us? Let's cut this graph into sections. From this portion, 0 seconds to 5 seconds. What is happening? Well, at 0 seconds, our velocity is 0. What does that mean? It means whatever object we have is not moving at all. I would also like to indicate that positive velocity is most often described as going right, and negative velocity is most often shown as being left. And we're going to use that standard today. So, we see over 5 seconds, our velocity increases to 10 meters per second. Let's describe this. At 0 seconds, we have an object at rest. Over the next 5 seconds, this object speeds up to eventually get to 10 meters per second. Now, this velocity is positive 10 meters per second. That means it's going right. Let's tackle the next section. From 5 seconds to 10 seconds, our velocity is now decreasing. How do I know that? Well, it starts at 10 and eventually finds its way to -5. That means our velocity is going down. So, at 5 seconds, we have an object going right at 10 meters per second. Over the next 5 seconds, its velocity changes to -5 meters per second. Now you can see how I've drawn this. This 10 meters per second vector is just about twice the length as this -5 meters per second. That should make sense because the magnitude of the first velocity is double that of the second velocity. And remember, when it comes to magnitude, direction does not matter. You should also notice that these arrowheads are pointing in opposite directions. That should make sense because we're now going left, which is the opposite direction of how we started at 5 seconds. Let's move on to the next section, from 10 seconds to 15 seconds. At 10 seconds, we're starting at -5 meters per second. By the time we get to 15 seconds, we're now going positive again at +1 meters per second. Our velocity has now increased to 1 meters per second. Now for the very last section, 15 seconds all the way to the end at 25 seconds. Now you can probably look at this graph and see that nothing's happening. It's staying constant. Does that mean our object is just not moving? No, that's not what that means. If this was a position time graph, that would be what it means. But our velocity time graph depicts something else. When the line is constant and straight, not moving at all, we're at a constant velocity. That means from 15 seconds all the way to 25 seconds, our velocity is +1 meters per second. So our object is still moving to the right at 1 meters per second, but it's not changing its velocity at all. Now that we've defined what's actually going on in this graph, let's talk about what it means to increase and decrease velocity and cross the x-axis, because that can be a little confusing. With this first section, it's quite clear what's going on. Our object is going from rest to 10 meters per second. It is speeding up, right? For those of you that have watched the acceleration video, you know that this object has a positive acceleration. So from 0 seconds to 5 seconds, our velocity goes from 0 meters per second, or rest, to 10 meters per second with a positive acceleration. How do I know our acceleration is positive? Because it's speeding up in the positive direction. Remember, positive is right. Now, what about this next section? At one point, our velocity becomes 0. It's at rest. What exactly is happening in between this section? Well, we start at 10 meters per second. As we go down this line, we are eventually going to end up at rest again. Now, how does that happen? Well, in this section, we have a negative acceleration. We are going to slow down. We're eventually going to slow down so much that we end up at rest again. But that's not the end. We continue this path all the way to -5 meters per second. Now, how is that happening? Well, let's start from the beginning. We go from 10 meters per second. We're slowing down. We're getting real slow over this entire section until we eventually get to rest, or 0 meters per second. Now our object is just standing still. Nothing's happening. It's at rest. But we still have a negative acceleration going on. This entire path has a negative acceleration. So now what? We're at rest. What does a negative acceleration do? We've already slowed down the maximum amount possible. Well, after we get to rest, our object is going to go in the negative direction. It's going to start going left. This entire time, it's been going right, but slower and slower and slower until we get to 0 meters per second. But now it's going to start going in the other direction because of that negative acceleration. And it's going to start speeding up in that direction. Now, that's a little confusing, but it'll get clearer. Because think about this. We're starting at 0, and eventually we get to -5 meters per second. Across that interval, this object is going to have to speed up. Otherwise, how is it going to get to the velocity of -5? So throughout this section, we start at 0, and then we start going left and speeding up in the left direction. Now, for the next section, we have a similar situation. We start at -5 meters per second, but now we have a positive acceleration again. Now, how do I know that? Well, in this section, we're once again gonna hit rest. We're crossing the x-axis. And the only way to do that is for our left-moving object to slow down. And remember, left is negative. So if our leftward moving object is slowing down until it reaches rest, we must be having a positive acceleration to counteract the negative velocity. Once again, after we hit rest, we're going to switch directions back into the positive. So, this object is going left, and it's slowing down, and it's slowing down, and then we get to rest. It stops for the briefest of moments. And then it starts going back right. It changes directions, starts speeding up, but only for about a second until it settles at 1 meter per second. For the next section, our velocity is constant as positive 1 meter per second. Now, that's kind of self-explanatory. We accelerated our object a whole lot around this path. It's been moving, it's been grooving. Eventually, we stop giving it acceleration, and it just keeps going at the velocity it was, 1 meter per second. It goes that for 10 whole seconds. It just keeps on moving. Nothing is happening. Its velocity is staying constant, so it's still moving because it has a velocity. It's moving to the right at 1 meter per second. It's moving right because it's a positive velocity. And nothing's going on. Quite simple. When you got constant velocity, life is good. Life is fun. You know what's going on. Life is incredible. Now, we've traced this path pretty thoroughly at this point, but just to hammer it in, I'm going to go over all the combinations of acceleration and velocity. And that'll make sense in a second. So, let's say we have a positive velocity and a positive acceleration. What's going on? Well, velocity is positive, and as we've said, that means it's going right. So think of an object, it's moving right. Great. But we are giving it an acceleration in the positive direction. Also right. So what's it doing? Well, acceleration, by definition, is the change in velocity. So if our acceleration is positive, our velocity is changing positively. It's increasing. So, just like in this section right here, it'll be speeding up in the positive direction. Now that should make sense. Our velocity is positive, our acceleration is positive, so it's going to speed up in the positive direction, in the right direction. Now, let's switch these signs up a little. Let's say we have a negative acceleration now. Ooh, threw a wrench into the mix there. Getting complicated now. So we still have a velocity that's positive. Our object is still moving to the right. However, with a negative acceleration, what's it doing? Well, our object's moving right, but our acceleration is going left. It's going negative. So our object that is moving right is going to start slowing down until it eventually reaches zero. But that doesn't always happen, but it can. So, object is still moving right, or in the positive direction, and it's slowing down. Okay, let's go to a different combination. Let's keep acceleration as negative, but change the velocity also negative. Now, what's going on here? Well, it's actually extremely similar to having both positive. Because let's think about this. Our object is now going left. It's going in the negative direction, all right? We also have an acceleration pointing in the negative direction. So what's going to happen to this object? It's going to start speeding up in the negative direction. It's going to start going faster and faster, just left. Instead of speeding up to the right over and over again, it's now starting to speed up in the leftward direction, in the negative direction. So, object speeds up in the negative direction. All right, last combination. Let's say velocity is negative, but acceleration is positive. Oh boy, last one. Our object has a negative velocity. It's going left, but acceleration is positive. It's going in the opposite direction. Now, this is very similar to having those signs be positive and negative, but opposite. our object is going left, and our acceleration is pointing right. So what's going to happen here is that our velocity is going to start going towards 0. It's going to start slowing down. Why? Well, think about this. Let's say we have a negative 2 meters per second with a positive acceleration pointing this way. Over time, that velocity is going to get more positive, right? So it's going to get to negative 1 meter per second. It's going to negative 0.5 meters per second. And then it's eventually going to get to 0 meters per second. So, negative velocity, positive acceleration, object moving in the negative direction and slowing down. Awesome. Okay, for an xt graph, we could find delta x over delta t, right? And this equaled average velocity. Now, what would happen on this graph if we did delta v over delta t? Take a second to think about this. What would we get? Well, hopefully you paused and figured it out, but we're getting acceleration. That's right. Specifically, average acceleration. Why isn't it just acceleration? Because we're taking it over a period of time rather than at this one instantaneous moment. And don't worry, we will eventually do that. But that's a calculus problem. We're doing physics. Physics is so much cooler, right? So let's find the average acceleration of every section on this graph. So, from 0 seconds to 5 seconds, delta V is going to be 10 meters per second minus 0 meters per second. Remember, final minus initial. Delta T is going to be 5 seconds minus 0 seconds. Do not forget to put units on this. Why? Well, if you don't put units, you're just going to get a number, which is lame. And also, if you don't put units, if you get an answer, you're just going to have an answer. You're not going to know what it means. So let's figure out what this means. 10 minus 0, 10 meters per second, over 5 minus 0, 5 seconds. That equals 2 meters per second squared. This is our average velocity from 0 seconds to 5 seconds. Great. Now, what does this mean? Well, we can see this acceleration is positive, correct? No negative here. Positive. And we also see, just from the graph, our velocity is going to be positive this entire time. It's above the x-axis. So, positive velocity, positive acceleration. What does that mean? Go deep into your brain, dig out the answer. It means our object is speeding up in the positive direction, which makes sense. It goes from 0 meters per second to 10 meters per second. That makes perfect sense. Great. Now, let's go to the next section. Little spookier. So, delta V over delta T. Delta T is easy. Let's do that first. We go from 5 seconds to 10 seconds. So, 10 seconds minus 5 seconds. Final minus initial. Great. Now this velocity is our final. It's actually negative 5 meters per second minus our initial velocity, 10 meters per second. Okay, so negative 5 minus 10, negative 15 meters per second, 10 minus 5, 5 seconds. That gives us negative 3 meters per second squared. Our average velocity from 5 seconds to 10 seconds. Now, what does this mean? Well, we got negative 3 which means we have a negative acceleration. But at the beginning, we have a positive velocity. So what's going to happen? Well, we're going to keep going in the positive direction. We're going to keep going right. But because of this negative acceleration, we're going to start slowing down until eventually we hit this time and we get to rest. Our object rests for a little second. But then what happens after that? We still have a negative acceleration, but we're starting at 0. Well, we have a negative acceleration and we start at 0. Our velocity should be getting more negative, right? Well, that's exactly what it does. Maybe it starts at this, gets a little faster, eventually getting to -5 meters per second. We start speeding up in the negative direction. All right, cool. So, let's move on to the next section. Delta V over delta T. Delta T is easy. Let's do that. 15 seconds, 10 seconds. Final minus initial, 15 seconds minus 10 seconds. Final velocity, 1 meter per second. Initial velocity, minus -5 meters per second. Okay, 1 minus -5, that'll be a positive then. So 6 meters per second. 15 minus 10, 5 seconds. And you can keep this as 6/5 meters per second squared, or you can get the fraction, which is 1.2 meter per second squared. So we have a positive acceleration again. Awesome. But we started at a negative velocity. So what's going to happen? Our velocity is going to get more positive. It's going to get more positive, more positive, more positive. And for a negative number, that means getting closer to 0, which means our velocity is going to approach 0 and our speed is going to be going down. We're going to start slowing down, slowing down, slowing down, slowing down, still going left, but slowing down, eventually reaching rest right about there. And for a little bit longer, we still have our positive acceleration. We start at 0. That means our velocity is going to get more positive, which means it starts speeding up in the positive direction, speeding up going right. Excellent. Now, this next section is going to be real simple. We can see this from the graph that it's going to be 0 acceleration, right? It's not changing velocity. But just for the sake of it, let's do some math. Time, 25 seconds minus 15 seconds. Velocity, our final velocity, 1 meter per second. Our initial velocity, it's also 1 meter per second. Take a look at that. 1 minus 1 is 0, so our average acceleration is 0 meters per second squared. What does that mean? Well, acceleration is 0, our velocity is positive, nothing's going to change. Our velocity remains positive, remains at 1 meter per second, and our acceleration is 0. Pretty simple. Pretty easy. Life is so nice when we got 0 acceleration. The math becomes real simple. Now, you may have noticed something while we were doing all that math. Our first acceleration here is 2 meters per second squared. The next one was -3 meters per second squared. Next one, 1.2 meters per second squared. And our last one, 0 meters per second squared. Take a look at these numbers. Take a look at the graph. Do you notice anything? I do. I notice something really big, really cool, really exciting. These numbers are actually the slope of the graph. Don't believe me? Take a look at this. This first section right here, we got an acceleration of 2 meters per second squared. The slope of this line right here is indeed 2. For this, we got a slope of -3. And guess what? Our acceleration is -3. For this, our slope is 1.2. And our acceleration is 1.2. For this, there's no slope. Slope 0, no change. 0 acceleration. So, what does this mean for us? It means for a VT graph, slope is acceleration. Now that's awesome. Another thing we can get from this graph. Lovely, lovely, lovely. You love to hear it. So much we can get from the VT graph. Let's say you're asked if the acceleration is positive or negative in a certain section. You can just look at the graph. You don't even have to do any work. See, this is going up. Positive. That's a positive acceleration. This is going down. Negative acceleration. This is going up. Positive acceleration. This is going nowhere. 0 acceleration. You can just look at the graph, take a little glance, and you have your answer. Now, if they ask for the number, you're going to have to do some math, but all you have to do is find the slope. That's algebra. You can do algebra. You're physics students. So, that's really cool. It's also really, really important. Remember how the xt graph, our slope was actually velocity? Well, for VT graphs, our slope is acceleration. Well, what's the connection there? Well, if you're taking calculus and you know a little bit about derivatives and integrals, you know that the derivative in terms of time of x is velocity. The derivative in terms of time of v is acceleration. So slope is derivative. Slope is change in time. Derivative is change in time. Pretty cool. You can also say that the integral of AT is equal to VT. The integral of VT is equal to XT. Whoa, 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 whoa. Hold on a second. You're telling me the integral of VT is XT? That seems important. We're working with VTs here. We're working with velocity and time. And I can get XT from this? How does this work? Well, just like how derivative is slope, integral is area under the curve. Well, what does that mean? It means, let's say I'm doing 0 to this time right here. This whole section here, blah, 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 all my squiggles. That's the area under the curve. And apparently, the area under the curve is xt. What does that mean? What is xt in this scenario? Well, it's actually distance traveled. Not particularly position. Distance traveled. Let me write this again. The integral of VT, aka area under the curve, is distance traveled. Excellent. Okay. So, let's take this first section of 0 to 5 seconds. I'll shade in this area right here. Now, if we take the area of that, which you should know how to take the area of a triangle, 1/2 base times height, so 1/2, 5 seconds, times 10 meters per second. That's area, 1/2 base times height. We get, what do we get? We get 25 meters. So, in this section, from 0 to 5 seconds, our object traveled 25 meters. That's pretty cool that we can do that. That's kind of awesome. That's really cool. That's really important that we can get distance traveled via area under the curve. Let's try it one more time. Let's try from 5 to 3.5 seconds. This area right here. So 1/2 times that's not 3.5. That's 8.5 seconds. So this little area is 3.5 seconds. So 3.5 seconds times 10 meters per second. Let me get out my handy dandy calculator. And that's 17.5 meters. So in this section, from 5 seconds to 8.5 seconds, our object moved a total of 17.5 meters. Pretty cool. And we can do that for any area under the curve. But you might be thinking to yourself, what about this next section? What is all this about? It's below the x-axis. Well, let's get the area and just see what we're working with. Now, this is not an equilateral triangle, so we're going to split this up into two different triangles. I'm just going to move this work over yonder. Oop. Over here. So, for this first triangle, this is 8.5 seconds. So, this triangle will be 1/2. The base would be 10 minus 8.5, which is what? 1.5 seconds. And a height of 5 meters per second. Now, wait a minute. What does that mean? I just put 5. Ain't it -5? You're right. It is -5. But for this purpose, we're going to keep it positive. And I'll talk about this at the end of this video. So, using my handy dandy calculator, we get 3.75 meters. So within this little triangle, this one right here, that's not clear, this triangle highlighted, it moved 3.75 meters. Let's do the next triangle to get this entire area. And this is 14 seconds right here. So 1/2. And that starts from 10, so 4 seconds. And the height remains 5 meters per second. Handy dandy calculator, but you could probably do this by hand, but I'm lazy. 10 meters. Cool. So the distance traveled, remember distance traveled. This is not displacement. Not yet. But the distance traveled within this entire section here is going to be 10 meters plus 3.75 meters equals 13.75 meters. Cool. Distance traveled. That means just how far that object moved. But, like I said, isn't it -5 for the height? Yes. So what does that mean? We have a negative velocity. That means our displacement is going to be negative 13.75 meters. Now, what's the difference there? Remember that distance traveled is just how far this object is moving along its path. Our displacement is going to be distance from its starting point, right? So how can we use this to get displacement across this entire section, right? Well, from earlier, we found out that this first positive red triangle, the distance traveled was 17.5 meters. And that was in the positive direction. Why? Positive 10 for that height. But we now have a negative distance traveled. Oh, catch me there. I said that wrong. Not negative distance traveled. Negative displacement. Distance traveled cannot be negative. Distance traveled cannot be negative. Distance traveled cannot be negative. Put that in your brain. But we had a negative 13.75 meters. Which means, handy dandy calculator time, our total displacement for that entire section was positive 3.75 meters. Ooh, you almost caught me forgetting the units there. Now, what does that mean in terms of what this object is doing? Well, it means that from this point, from 5 seconds, all the way to this point, 14 seconds, this object moved right, it moved left, it moved right, whatever. It moved everywhere. That moved in all of its distance traveled nonsense. But at the end of it all, it landed 3.75 meters to the right of where it started. Pretty cool. Pretty cool. This is some cool stuff we're doing here. This velocity time graph, so helpful, so cool. You can get so much out of this. So, to summarize, you can take the area under the curve of a VT graph to get distance traveled if you ignore negatives, and if you keep the negatives, you can get displacement. Very cool. Now, this was a pretty complex video. So, just for funsies, we're going to end this video off with something simple. Very simple. Why don't we try and find the distance traveled from 15 seconds to 25 seconds? Take your time, pause the video. Okay, we're back. So from 15 seconds to 25 seconds, what do we do? Well, remember, distance traveled, ignoring negatives, is the integral, is the area under the curve. And what's the area here? It's a rectangle. I sure hope you know how to take the area of a rectangle by now. It's just base times height. So, the base, 25 seconds minus 15 seconds. That sounds like 10 seconds to me. The height, 1 meter per second. That gets us to a whopping 10 meters. That means in this entire area, our object moved 10 meters. That was the distance traveled. And because there's no negatives, it's also the displacement from its original area, or from its original starting point. So, that was an overview of everything the VT graph has to offer. I hope this was helpful, and happy learning!